The next talk is called Semi-Interactive Simplification of Hardened Android Malware. Abdullah is the mobile security team lead of the company Adjust, located in Berlin, Germany, providing mobile analytics services and overseeing the security of mobile open source libraries integrated into tens of thousands of devices, hitting a total of more than 400 billion data points per month, which is a quite impressive number to deal with. He's researching on mobile advertisement fraud schemes and how to develop appropriate countermeasures. Today, he's going to talk about the omnipresent technique of binary code obfuscation, as far as I understood that, and semi-automated methods to simplify a hardened Android code base. So welcome, Abdullah. We're eager to hear your insights.
Hey, Eric, can you hear me? Is the voice okay?
Yes, the voice is okay, thanks.
Perfect. Just one thing about the title. Thank you so much for the introduction. About the title, me and my friend had a bet if we can make a tech talk with the longest possible title that we can, and I think I won. So, all right, let me see if I can share my screen. Can you see my screen? With a
yes,
huge
we can
title?
See your screen. Everything's working fine.
Perfect, perfect. Well, one second. Hello, guys. I would actually, it's a shame that we can't have a physical meeting, but I guess due to the times that we live in right now, we're just gonna have to settle for Zoom. My name is Abdullah Joseph, and today I would like to talk to you guys about something that I was researching as part of my job, which is usually looking into ad fraud prevention techniques. Because of that, most of the things that I look at are malware, adware, usually it's called in that space. And adware has some really interesting functionality. People usually do it without any interesting rootkits or jailbreaks that you can see exploits running in the wild. They usually use whatever it is that they have living off of the land. I guess that's what it's called. So you basically see them trying to install an application, an APK downloaded for the sole purpose of making what's called in the ad industry an install, which means that you can get attributed to a network with that money. And basically, if you keep doing this ad infinitum, I don't know, 1,000 times, you can make very good money. So this is the field of research that I work on. And today I would like to talk to you a little bit about some of the interesting malware that you can find, the 20 percentile, not the most of the ones that you see on the wild. These are the ones that you see that have really cool obfuscation techniques and software protection mechanisms behind it. This is the agenda for today. It does include a small demo, so I really hope that with the new laptop, because my laptop, my MacBook spilled coffee on it yesterday. This is a new laptop. I really hope the demo works. And if it doesn't, that's God just doesn't like me today. So without further ado, let's talk about software protection. So I met a few malware authors in my life. I don't know exactly how their job, their 40-hour week looks like, but I'm imagining it's something like this. So basically your boss comes and he tells you, you need to make something that works, something that can get us money through malicious ways, and it's undetectable. Why should it be undetectable? Because malware is actually detected all the time. TechCrunch loves titles like adware found in 200 apps in Google Play. 150 million people got impacted by something, and they keep giving it really cool names like Viking Horde and Simbad. So this is something that is always being countermeasured. As a malware author, you really need to start innovating in different techniques. This is not a how to become a black hat talk. It's not. This is something that basically using and trying to expose some of the techniques that malware and other good people use. So for example, you always see malware bites and snort and different IDSs trying to protect against such malwares, trying to protect against the signatures behind it, trying to, for example, execute it in a virtual machine, in a virtualized container, so that it sees the system calls that it does, and it categorizes it if it's dangerous or not. Win32 API is very good with that, because with Win32 API, you can even see functions like crypt encrypt. And if your friend shared with you a presentation about next quarter's fiscal year plan. I'm not a finance person. And that PDF file or the spreadsheet started calling crypt encrypt and mprotect and trying to allocate executable, readable, and writable memory ranges. Don't open it. So the thing that we're going to talk about today is software protection, and with the percentage of malware that deals with these techniques. Let me adjust the screen a little bit. And it's usually obscure techniques. It's usually things that you find on Freak magazine, if anybody is a subscriber. You usually find it in the really old HTML websites, techniques relating to code injection and code caves for ELF binaries and for PE binaries. It's not things that a lot of people try to, it's not things that you would find on just any regular blog, tech blog. And techniques that we are going to talk about today, it's used, for example, in stock trading companies. If you have a proprietary trading algorithm and that's your bread and butter, if that algorithm got leaked, there is a problem. You need to execute it on the cloud or on a client device. That's going to be a problem. There's really cool research right now coming up called verifiable computation and multi-party computation that actually tries to address exactly this problem. You have a function y, and it has an input x, and you want to execute that function without revealing too much about how it's done, and you just basically want to use a worker. There is research that's now happening about that. One of the most important things is game companies. I believe one time I read a tweet about the game creator, the game designer for BioShock, the original one, and they basically said that they achieved their goal of remaining uncracked for 48 hours. That was an understatement, but yeah, I mean, that thing happens all the time. People try to protect their proprietary libraries, their proprietary apps, but somehow, if you have an analyst that's dedicated and knowledgeable, it's gonna crack eventually. Weapon manufacturing is actually quite interesting. I stumbled upon this U.S. Army solicitation that says that anti-tamper technologies, AT technologies, should be providing protection against exploitation via reverse engineering. And the purpose in here is to add longevity. That's a very important word, longevity. You can't protect 100% a black box. That's not possible because you are executing it. Okay, it's executed on a host. And the idea in here is that you need to protect it against the host that you're executing. I'm giving you instructions and you have to follow those instructions. And if you have memory and if you know what I'm talking about, you can follow along and say, oh, this happened and then this happened and then this happened. That means that the user is trying to do this. The purpose of software protection is literally to go against that logic, is to try to make it as diverse and as diffused as much as possible so that the person who's executing the code doesn't know what they're executing. So this is the CIA triad: preserving confidentiality, integrity, and availability of data and algorithms, and it applies perfectly in here. So I have a quick example in here. I would have loved to do this with a live audience and ask them questions about it, but it would have been a lot nicer and more interactive. But I'm just going to stick with my monologue in here. So we have an example in here. This is x86, and no need to be a Jedi. Basically, the explanation is right here. So the first instruction would move 0 to EAX. It would test if EAX is 0, and if so, it will jump to this location. It's pretty straightforward. There's nothing too much about it. What happens if we do this? So let's try to go through it. We move 0 to EAX. We test if EAX is equal to 0. If so, we try to jump to hello. And then we're trying to move EBX to EAX. And then there is SIDT happening. And then we're trying to get system clock, which is what's happening. The idea in here is that this is all garbage that will never be executed, ever. X, Y, and Z are 100%, that you could fill it in there with data. You could fill it with bunny fufu instructions, whatever it is that you want. This code will live in the binary, in the .txt section, and the .text section, but it will never be executed. Why? Because this is a constant statement. It's called a positive opaque predicate. That means that it's always going to jump from here, from number 3 to number 4. Always. It will never look at X, Y, and Z. So you can throw garbage in there. That's an obfuscation technique. It's called dead code injection, as opposed to an optimization technique that's called dead code elimination, something what LLVM is heavily trying to invest their time on. So this is a technique. Why would I throw this in there? Confusion. Literally just confusing the analyst, trying to make it as hard and as annoying as possible to try to Google what the hell is SIDT and what's its relationship with the ABP register and why am I querying for this thing. This is simple to ignore because you see a jump Z hello in here immediately. If I throw those instructions in between 1 and 2 and try to make it a little bit more complicated, we might get to an interesting result. Let's take a look at this example. So I have in here a function. Don't ask me about the programming language. I think this is, this is C. Yeah, this is C. This would work in C. This would also work in Java, but this is C for now. So actually, Java doesn't have int type. Forget about it. So in here, we have a function called foo, and it takes 3 arguments, A, B, and C, integers. And then we do a Boolean, mixed Boolean operation in here, and we do a minus C. What's the result of this? Before anybody wipes out their Python calculators, it's 0. And this is very easy to interpret. This is very easy to do for a machine. This is very easy to do for a human with a calculator. It should be straightforward. And if we try to do something like this, which was very hard to write, this executes, and it executes well. And there is no problem. A machine will understand this. However, if I ask you right now, foo 1, 2, 3, what's the result? By looking at it statically, I don't think you can infer the result in here. It's still 0, by the way. This will evaluate to 0 with the arguments 1, 2, and 3. But right now, you just added it a lot of different layers of confusion. And this actually works. This is really complicated. If you ask any reverse engineer, and they would have a certain methodology of doing things. They would go static analysis maybe, or dynamic analysis, depending on your work. You might go for something in the middle, like executing it in a virtualized environment or emulation, for example. You might go for symbolic execution. There is a certain methodology, but if your methodology is relating to, I want to look at the disassembled or decompiled code, this will really hinder you. And the idea in here for obfuscation, software protection, binary hardening, they're all the same, is to make it functionally equivalent but harder to analyze. So let's talk about the next part of the presentation, automating analysis. So I'm a good guy, I'm an analyst, and I got handed a malware, adware, something, and they are using automated ways to create something like this. How would I try to understand it? How would I try to make sense of a certain operation that's happening? So let's take an example of this. This is Java, and I think anybody who looks at this with Java knowledge should understand what's happening. Basically, in here, you have a map. It's a hash map or a dictionary if you're a Python person. You basically put some keys and some values into the map. Here we put the key AAA with bunny foo foo, BBB with foo bunny foo. You get the point. And we make a post request with this IP address and with this endpoint. And that's pretty much it. We just pass these parameters into it. Now, without looking at make post request, without looking at it, if you're analyzing such a binary and you decompiled it and you want to understand what's happening behind it, you really don't need to look at make post request to infer what's happening in here. This is good so far. I understand. I wanted to focus on exactly the parameters that are being sent to this drop point. That's one way of doing it. Another way would be doing something a little bit more straightforward, like man-in-the-middle attack. You would attach a proxy in the middle of your host, and you run it on an emulator, or you just run the code, the binary itself, and you would analyze the request. For sake of simplicity, just for the sake of presentation, let's assume that man-in-the-middle attack doesn't exist. You see encrypted text, so you have to jump into the code, and you see something like this. What would happen if, right now, my goal was to understand the parameters. What would happen if you see something like this? And let's assume, just for just a thought experiment, that man-in-the-middle attacks is a little bit hard. Maybe this post request is AES encrypted. And you would have to dive into static analysis. You would have to dive into the code to understand the values that are being sent. And you see something like this. So basically in here, the first step I would do is I'm going to try to just take a cursory look at crypto.get. What's happening in here? And what are the parameters? What is the return values for crypto.get? I'm assuming it's not the same return value for different arguments. So if I give it different numbers, it would give me different return values. That's just an assumption. Let's actually take a look at crypto.get, and we see something like this. If the screen is a little bit too small, you're not meant to read it, but I'm just going to go ahead and scroll over it in here. We see an interesting Unicode byte array in here, character array. And we see some interesting things happening in here with XORs going on. And then we see things like this, plus 99, and we have some interesting fields that were, the names were automatically generated by my decompiler, and we see a switch statement that looks pretty readable. This is very, very readable. I can understand it perfectly. And we see some interesting predicates like this. And we move on to the third one, and you understood everything. And now you can come back to this and say, yes, crypto.get, when executed with 100, 200, and 300, it's going to bring us XYZ value. That's right now not possible. Static analysis just died immediately. This is, if you are an operating system developer or you work with compiler optimizations, this is a nightmare. I'm pretty sure this code is not optimized at all. But does it do the job that we are trying to make it do, which is functionally equivalent, but harder to analyze? Yes, it does. And there are obfuscators out in the world that actually do this, Java layer obfuscation. So now my next step as an analyst, I really still want to understand what's happening in here. I really still want to understand what are the values that are being sent. And again, man-in-the-middle attack is not an option here. So let's move forward. So the next thing I would look at is something like dynamic analysis. And there's a really cool tool called Frida, which I believe Mr. Gautam, the previous speaker for virtualized containers, did speak about. It's a very good tool. It's a very useful tool. I highly recommend it. And with this tool, you can do things like basically write a JavaScript script. And you would be able to hook into a function and understand what are the arguments and what's the return value. And this is a super simple presentation for this. This is, I think, the simplest one, the simplest script that you could write. You basically in here try to hook into a class and then hook into the function for that class. And you have this entire function callback as a implementation that will occur before the actual execution of the class. Actually, no, I need to correct myself because I use .implementation. This will happen in lieu of the actual crypto.get. So crypto.get right now is not going to get executed. This will get executed. What am I telling it to do? I'm telling it to just print called crypto.get. And then I wanted to run the actual implementation and print the arguments and the return value. This is pretty cool. It's pretty simple to do. And the result that I see is this. So I just tried to understand what 3 instances of crypto.get do. And I tried to run a semi-debugger to basically tell me what it's doing. And I was welcomed with this. This is 7 more times than what I wanted. As an analyst, I just increased the number of man hours I need to spend to understand what's happening in here. This is not so good because now I have to investigate other locations, and that's not giving me the result that I want. I want just to focus on those 3 instances of crypto.get, and I just want to understand what that post request is doing. I really don't want to look at 7 other instances. And I assure you, it's not going to be 7 other instances. It's going to be like 1,000 other instances. If you used an automatic obfuscator to obfuscate your code, it's not going to be obfuscating 10% of it or 20% of it. It's going to be obfuscating most probably 90% of it. So you're going to see a lot of this. So the next step that you could work with is that right now you have distinct numbers, right? So I have 100 being called in here, and a 200, and then a 300. And it's different than 231, 23212, 11, and 300. It's different, right? So we have a shared last argument, but the others are different. And I'm assuming that it's going to be different arguments are going to give me different return values. So since they have distinct numbers, maybe we can somehow trace the call stack, print the function arguments, and we'll be like, okay, if we find 100, 200, 300, then it belongs to key number AAA, key with AAA. And if we found it with something like this, it should belong to BBB, and we don't care about the 7 other instances. That's one way to move forward. And to do that, we actually have to print the call stack. Luckily for us, the printing the call stack is pretty simple. It's something that any exception in Java would do, and it translates 100% to Android. So I have this handwritten function, which I cropped in here for sake of readability, called getCallerInfo. It's very simple. If you just Google how to write an exception in Java, you could easily translate it in here. And I'm basically trying to print the call stack. I'm trying to understand where is it coming from. And maybe if I know where is it coming from, I know which function should I focus on and which function I should just ignore. And I executed it, and then I found that the execution is like this. All of them are coming from crypto.get. That's obvious because I'm hooking into crypto.get. All of them are being called with line number 1, 1, 1, 1. So that's a problem. And that's the disassembled Smalley. Smalley is a Dalvik bytecode representation language that you can use for disassembly. It's very useful if you want to do any sort of Android reverse engineering. And if I look at the code, I see that there are dot line directives, they call them. And they are all the same. And this is allowed, unfortunately, in the Android ecosystem. You can have duplicate debug directives. And the idea in here is that there's only one limitation, which I just highlighted in here, that the line register represents source line should be associated with the next position table. It should always be a positive number. That means that 0 is not allowed, but anything less than 1 is not allowed. But apart from that, you can have duplicate numbers. That's possible. I will show you right now a demo how this is very much possible. So we've reached an interesting point. We have 10 instances of crypto.get that we really don't care about. And we only have 1 that we care about, 3 that we care about, actually. How do we move forward from here? One option that we can do is something called relining the APK. This is not a common technique. I actually didn't find any tools for it. And the idea in here is that you can basically try to reline all the numbers that are there so that they are sequential instead of being duplicates like 1, 1, 1, 1, 1, 1. I don't think I have too much time for this, so I was supposed to show 2 demos. I will only show 1, and if we have time, I will get back to the relining demo. But right now, let's just move forward with the presentation, and later, if the Q&A was short, I can try to execute this demo. So let's go back to the next steps. We tried to understand which this crypto.get business. We hooked into it, and we saw it's being executed multiple times. We tried to get some sort of a call stack to see, okay, it's being called from this function, so we can just analyze this function at this line. And that failed because they were all executing in the same function and the same line. So the next step would be that, as I said, somehow relining the code base. However, what I would like to see as an analyst is that I would like to basically execute the code. Just execute it once, run the code base, and then have it being annotated. Basically, by annotating, I mean some sort of a comment, some sort of a comment of the execution flow. There are a few tools that do this. There was a tool called FinRes long time ago. It was using ptrace to actually do that. The tool has been discontinued. I found it in archive.org. There is no trace of it on GitHub or anything like that. There is a tool that does this. It's a layer on top of GDB called GIF, G-E-F, and it has a function called trace-run, and it will do something like that. However, both those tools run native. I want something that could run on Java, on a virtualized, the Java virtual machine, and give me something like this. Basically have a get, which is the name of the function I'm calling, with the arguments that I'm calling, and gives me the return value. Perfectly clean and perfectly readable. I don't care about recompiling the code base. That's not my intention. My intention is to basically just annotate these execution flows and try to understand them for myself as an analyst. Write them in my report, for example, for a specific run. So if I execute different buttons in the program, it should give me different results. So that should be a different code base. That's the situation I would like to see as an analyst. And now we have the demo. I think I don't have too much time, but I'm hoping I can try to show you guys how this works. I really hope everybody can see my screen and i3 didn't die on me. Right, so I'm just gonna run the test suite for the project that I'm working on, which is the Cryptocon. And it failed miserably. Right, Android home equals, where did I save it this time? That failed. Let me see if I can show you the result of what this is going to happen. Yeah, the demo, I have Android Home. I forgot where I actually installed it. And this is a new computer. So if I start right now fighting with it, I assure you it's going to be 20 minutes with you guys looking at me and it's not going to work. So I'm just going to show you the result of what it's going to do. So the result is you would execute it with something like, and there is a README in the project that I'm working on, that will actually show you the execution environment. So you would have to run something like this, basically. You would run an emulator. You would run a script called install Frida server. Both of those are included in the project. So all you have to do is basically just copy paste this line and this and run it, and it should be okay. And it should install all the dependencies for you. And then you would run something like this. In here, you would specify the APK that you're working on. You would specify a hooks file, and this hooks file should look something like this. Let me zoom in a little bit on it. So this is basically the Radare2 representation of how that function should look like. So if you have a function called cryptor get, it should look like this. JNI uses the same thing. Actually, Radare copied it from JNI, and you can get this thing from practically any decompilation tool, JADX, APK tool, anything like that. It will give you this function signature. And you can put as many functions as you want in here, the things that you're interested in, the things that you would like it to be annotated. In our example, we only cared about cryptor.get. We didn't have second and third. And then you would run it with something that looks like this. Let me jump to the result right now. The result of this thing would look a little bit like, let me zoom out a little bit. Temp Smiley main activity. I really hope this works right now. It does not, because I didn't run it. It's a new computer and I didn't run it. So this bombed right now. So that's what I'm telling you. The demo gods didn't like me today. So what I'm going to show you is that it's going to look something like this. Ideally, I have on my website, which I'm going to have a link to, a video of this thing. It's already live. You can go and check it out. And there is a PDF of a fat presentation that includes a lot more context of what I'm talking about. So it's basically, you can consider it kind of an appendix to this talk. And this is how it should look like. It should basically be annotating it with this prefix, and it will give you the function argument in here with the return value. And that's the entire purpose of this tool. It started out basically as a tool that I wanted to do for my own job to tackle layered Java obfuscation. So if you have something that is doing some sort of a string obfuscation like what we're seeing in here with crypto.get or something like that, there are commercial obfuscators that do that. And it will tackle something like realigning all the code base. This is what the tool was supposed to handle. I'm very happy I used it in at least 5 malwares right now, and it works just fine. And the idea behind it is that it will automatically do all of this for me so that I don't have to worry about it. I will just go into static analysis. I will stop at this location right here, the initial slide that we had. I will see this, and then I wouldn't have to worry. I will just basically run it against the signature of crypto.get, and it would work automatically. I don't have to worry about myself diverting attention to 7 other instances, or having to worry about how to set up Frida, or having to worry about the emulator that I'm working with, and x86, does it have an x86 or does it have an ARM architecture? I just want to worry about this exact point, and that's it. And this is what the tool is trying to do. It basically parses an APK and realigns it entirely. It has a built-in Smalley parser, and it's trying to actually handle it so that I can show you this. If you see in here, .line 1. So as you can see in here, this is a disassembled APK that has multiple line ones. Actually, all the lines are number 1. There is an issue that you're going to get if you're trying to just use it with like a bash script that runs SID, and you just try to sequentially put all the lines, is that you can have multiple, and this is very legal, you can have multiple invoke virtual in here. That's not a problem. If I recompile the code base right now, this will work just fine. I hope so. This is a problem because if I'm trying to hunt down for the specific crypto.get instance that is in between line 2 and line, for example, 3, remember it should be sequential, I will get 10 instances of, well, not 10. I will get 6 instances of the function that I'm trying to hook into, which is a problem because I only want one line to correspond with one instance. It will make a lot easier sense for me to understand it like that. So the tool actually goes through every single line and try to see if it's illegal or not. For example, you can't put lines in the middle of an annotation block. And it will try to have a threshold of usually 2 lines. You can, of course, customize it to have it in between each line. It will have something. That's the idea of the tool. Using something like SID or just a simple Python script that tries to sequentially change everything didn't work for me, because the malware that I was looking at, it even used reflection and string obfuscation with reflection to try to call methods. So literally every single function call in there was reflected in a specific hotspot of the program. And every time you try to do anything, there is always a call to crypto.get. There is always a call to a reflection afterwards, and it's always realigned. And they were using opaque predicates. That means that there were junk code. You remember that dead code injection technique? They were using it. So it's even bloating the code base even further. Looking at it gave me a headache. So the tool that I wanted to use, oh, by the way, realign is an actual word. I didn't invent it. I almost started using it in the company and nobody believed that it was a word. Thank you, Merriam-Webster. So the idea behind it is that I needed something that is simple to use and could be reproducible by anybody later. And this is the tool that I came up with. The idea that I would love to have behind it is to include more simplification techniques. And this is where you guys come in. The idea is that I would love to get some more emails, issues open on the GitHub repo that tells me what other deobfuscation techniques that you try to use. Could something like this work with it? There is a lot of automatic deobfuscators that are out there. I have a slide after this to show it. However, the ones that I used didn't fulfill this purpose for me. I needed something that could be used by an analyst for specific cases. In this case, layered Java obfuscation. It would be really cool to use some sort of a symbolic execution engine like Anger or Miasm. Using something like that, you could even try to simplify crypto.get. So if you actually would like to understand the algorithm for crypto.git, which looks like Egyptian hieroglyphs, ideally you should use a symbolic execution engine that could give you instructions that are easier to use. If you want to replicate this thing, if what you care about is crypto.get, not for example, make post request. That would be something cool to see. And I did mention about sharing your experiences with me, and that's pretty much it. Sorry guys for the demo, that actually sucked, but yeah, I mean, spilling coffee on the laptop kind of ruins the motherboard. So I'm happy my colleague let me lend his ThinkPad for this talk. This is, I think, the last slide. It's similar work to the things that I just mentioned in here. Both of those repos, Simplify and Dex Oracle, were made by an amazing person called Caleb Fenton. Very, very smart guy. Decrypticon, the tool that I was supposed to show you, is taking a lot of influence from Dex Oracle. And the idea behind it is that Dex Oracle does some static Android deobfuscation rather than running it once, running the entire execution flow, and then trying to understand the arguments and the return values. There are some cases where, for example, if you have a bloated code base with multiple positive and negative opaque predicates, basically dead code all over the place, Dex Oracle wouldn't work. There is another tool made by, I can't remember the name. It's a very famous tool. It's called Dex Hunter, and it does automatic Android unpacking using some really simplified generics. For example, if you have something like mprotect, it will try to map an executable, writable, readable range of memory, and then it will try to unpack the code there. If you're working with a sophisticated packer, it should do something a little bit more complicated. Dex Hunter works a lot. I used it a lot in the wild. So the semantics behind the work that I tried to do, I tried to adapt the same flow that those three projects had. They don't replace, the project that I made doesn't replace those. I believe that it could be used as a, there was a scene in The Matrix, really cool, where Morpheus, Trinity, and Neo went to the Matrix, and then there was just rows and rows of guns all over them. And when Trinity asked Neo, it's like, oh, what do you want? And he said, guns, lots of guns. This is exactly the same case. You have multiple guns. You're an analyst, okay? You need more than one tool to do the same job. Because when one tool breaks, the other hopefully wouldn't. This is what I try to think about these projects. And it would be nice to see more projects like this, actually. And that's pretty much it, guys. Thank you so much. This is the repo that I was telling you about. Let me know if there's any issues with it. I'm trying to be active with open source communities. This is my Twitter. You can reach me out with any issues that you have. And as I mentioned, the slides for this presentation and hopefully a video of the execution will be on the website, my website, malwarecheese.com. And we are hiring on Adjust. So if you would like to work with some interesting adware fraud prevention techniques, you're good with C, you're good with binaries, please reach out. Here's the channels that you can find me at. Many, 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 many thanks. Thank you, Android Security Symposium, for allowing me to present. And now I think the Q&A is up.
Okay, thank you very much, Abdullah. Now that my audio setup seems to work as intended again, we're ready to continue with the Q&A session. Once again, you can raise your hand in Zoom in order to ask your question using audio, or simply type it into the Program Day 1 Q&A channel in MetaMost. So until people are going to start typing, I would like to ask a rather general question. So as an analyst, what do you think is the most, I'd say, nerve-wracking technique regarding obfuscation? Is it that code injection?
No, it's not. The most annoying tool that you can find, and I can safely say that if you find it, you're going to spend a very, very, very long time analyzing a very simple block, is virtualization. And something like mixed Boolean algebra, which is a technique that there's a really cool talk from Ruhr Universität Bochum and CCC by a person called Tim Blastico. I really hope I'm not missing the name. The name of the talk is called Modern Binary Obfuscation. It's very easy to find. It's from Chaos Computer Club. And he mentioned really cool techniques regarding mixed Boolean algebra that breaks symbolic execution engines. So your last case scenario, after static failed and dynamic failed, you want to analyze the simple block. And you would have to go for something automatic like symbolic execution. These techniques are meant to even break that. So I would say virtualization and something related to compiler de-optimization is the most annoying two things that you can find. And weirdly enough, it is actually easy for a defender to create those. If you know good enough development, you can. So those two things.
Okay. And another question. So from your practical experience regarding that code injection, once again, how much would an application's machine code or bytecode for that matter grow in size typically? So from a practical point of view regarding obfuscation tools which are readily available out there, are there any experience values to this?
How would it grow in size? So can you see my screen?
Yes, we can see your screen.
Perfect. Let's look at something like crypto.get. For example, crypto.get, what it does, at least what I understood it should do, is basically try to match characters in here, Unicode characters, with each other based on whatever it is that you're passing. So if you're passing it 100, it will loop with a modulus over a specific number. I extracted the number once, I think it was 128 in here, and it will just basically loop over it and keep extracting it. So this entire function could be simplified by like 4 lines of code with the exclusion of the array. And you can see in here that it grew in size quite a bit. There's really no limit to that code. However, I can say that most of the malware I encountered had a very specific section that they highlighted with all the techniques. They threw everything there. There's a really cool paper about obfuscator LLVM, the original OLLVM paper, and they measured, they had a pass in there, a compiler pass called bogus control flow, and they basically do something very similar to this. They measured the increase in speed, sorry, the decrease in speed, and it was with all 3 passes that they had was 1.25x more than the original execution. So it's heavy, but if you try to control it, you can really try to reach a very nice sweet spot between functionally equivalent and still secure enough to not have an analyst break into your stock trading proprietary algorithm. It's the original paper from OLLVM that they had those speed tests. So you can check it out. I can share my screen. It's for those of you who don't know, if you just Google OLLVM, you're going to see in here obfuscator LLVM. And I think you can find it, yeah, right here. This is the paper. I think it should be on Springer or something like that. You can easily read it as a PDF and you will see it. It's not too old as well, so.
Okay, thank you very much for that. We do have another question from Markus Vogel. He asks, how common are anti-analysis methods like detecting Frida, exposed, or debuggers in the wild? So codes that behaves differently in these environments or when they are detected.
I'm sorry, I didn't understand the question exactly. Can you repeat it?
Yeah, sure. How common are anti-analysis methods, like programs trying to detect tools like Frida or exposed or debuggers?
Oh, okay.
So that the code behaves differently inside these environments or when they are detected.
So they are common. They're very common, actually. Like one of the most common things you can do to deter a debugger is something called the ptrace attach trace me trick, which is basically you have the binary trace itself, which means that no other debugger could hook into it. That's the most common one. You find it a lot, but honestly, my old mentor told me if you're running with a debugger or something like a debugger like Frida or exposed, you're in God mode. There's nothing, there is nothing that you can run away from, because if you have a ptrace method that tries to hook itself, all you have to do in a debugger is just break into ptrace and then nop it, and that's it. You're done. And you can even move it to your disk, and you can have your friends execute it, and it's just a dead technique. So it is very common. You see it a lot, especially the ptrace attach trace me. I even think MSTG, OSF MSTG has that technique, if I'm not mistaken. I think they do. So it's very common to see it. It's even in OSF, but breaking it is, for a talented analyst, should be not, it shouldn't take too much man hours from them, as I believe.
Okay, thank you. Any other questions? Let me see. Okay, so I would have one more question until the next talk starts. So from my very sparse experience in reverse engineering, doing that using Smalley code is considerably more doable than x86, I would say, x86 assembly. And maybe for that reason, I don't know, it seems that obfuscation is more widespread in the Android world. Would you agree to that from your practical experience?
I do agree. x86 is not fixed size instructions. ARM is fixed size, so it's a lot easier to edit a binary, if you want to say, basically try to inject things in the middle. But with x86, it's not fixed size. So if you try to inject something, you're going to have a horrible time working with relative offsets for the jumps. You basically broke everything. So if you just, I'm not joking, if you just insert one single knob, you just broke all the jumps and the references. And LLVM and GCC try their best to optimize things. So you're going to have a very hard time with doing it with x86. The best thing I would suggest is, if you target native, is to do it from the compiler side. So you can take something like tiny_cc, a very small C compiler, and you can hack it. That's possible. Mobfuscator, it's an obfuscator that turns all instructions to mov. It's amazing. It's just beautiful. It hacked tinycc. The person who did it hacked tinycc to do it, which is just the most genius thing in the world. With Java, you still have jumps, but it's sorry, with Dalvik, you still have jumps, but it's a lot easier. And I can imagine that you can do binary editing a lot easier in there than in something like a compiler optimization. But then again, you have more people who understand x86, historically speaking, than you do people who understand Dalvik. So there is a trade-off, I guess.
Okay, so one final question. We are already a little bit over time. Eduardo asks, do you consider that virtual machine obfuscation can be attacked in Android in the same way as you would do on Windows?
Mm-hmm. Yes, you can. One of the most famous VM protection, commercial VM protection tools that you can use is two, Timida and VM Protect. Both of them are Windows. Some people try to port it into Android. You basically should use the same heuristics, the same analysis methodology. You try to understand the handlers, try to understand where's the fetch, decode, execute loop. I would even say it's simpler on Android because Android ecosystem doesn't give you a lot of room to play with. You can't run, it's very hard to run a different process on Android. If you're an app and you try to run a different process, even if you look at the fork import from Bionics libc, it's not really forking, it's cloning. It's cloning the thread into something else. Forking is not so easy to do, and it's not very, it's not recommended by the Android developers, the people who created Android operating system. So I would say it's even easier to do it because you don't. For example, I doubt any virtual machine obfuscation technique would try to do something like a just-in-time compiler in Android. They would do something simpler like interpretation or something like that. So it's a lot simpler, I would even say.
Okay.
I hope that answered the question.
I guess so. Abdullah, thank you very much again for your talk. This was very interesting.